It's better? Yeah. Yeah, so hi, everyone. My name is Artem. I will talk about our work studying fluently group generators. And this is a joint work with Anna, Ivan, and Arnold from Delta Lab and from Vienna University. And yeah, let's start. So probably because this is a geometric deep learning reading group, I don't need to tell that symmetries are everywhere, and that's very important. So I will just leave here this quote that the universe is an enormous direct product of representations of symmetry groups by Nobel Prize winning physicist. I think it's a really nice quote, and maybe we should put it more in our papers. But yeah, symmetries are everywhere in molecules, in dynamical system, in a physical system, in images, etc., etc., etc. So neural networks, as universal function approximators, learn the symmetry if they're useful for downstream tasks, and if the symmetries help to explain variations in the data. For example, it has been shown that an unconstrained network on the task of image net classification, it learns scale symmetry, it learns hue symmetry, it learns rotation symmetry, and a bunch of other symmetries. It also has been shown that such networks, unconstrained networks, they often just learn different orientations of filters. That is to say, to encode the symmetry into their weights. So understanding this process, the symmetry learning, is essential to provide a good interpretability of those models. So the first question is, why do we want to have good interpretability of symmetry learning? So the first answer could be that knowing learned symmetries can help you to better understand your data. So imagine if you have, for example, such task when your model tries to predict the diffusion of this heat circle, and you have two cases, on the top and on the bottom. So if your model learns the dynamics on the top, then you can say, like, okay, you can analyze it. You can say, okay, here is rotation symmetry, and from the rotation symmetry, you can make a conclusion that, okay, this diffusion has uniform diffusion coefficients. So you kind of can understand something about your data by looking at the symmetries. And yeah, in the bottom case, it's vice versa. You can analyze it, you see there is no symmetry, and thus the diffusion coefficients are not uniform. The second application of that would be, sometimes we need to verify what our model has learned. So imagine you're a machine learning engineer and you're working on something like histopathology analysis. And in histopathology analysis, we know that we want to be rotation invariant. So if someone gives you a network and tells you that, okay, this network solves this task very well, you want to verify it somehow. You want to actually see if it's invariant and what it is invariant to. So that is verification. The next question would be of how do we do this interpretation of the symmetries? I would divide existing methods into three families. The first one is the family of methods which relies on architectural modification. You may be familiar with conv layer. In general, those types of methods, they try to design layers of the network which learn some form of symmetry generator exactly directly from the data. The second family of methods, it takes the network and it examines the network with respect to some predefined transformations. So you like sample different transformations, you define some distributions of this transformation, and then you see, and then you somehow morph the distribution to show to which transformation the network has become invariant or equivariant. And the third family, I would say, is the most powerful family of methods, which involves manual identification of symmetries. So, for example, this is a very nice paper by Ola on DistalPub about natural accurate equivariance in neural networks. So they just they do backprop for the networks, and they retrieve the patterns which trigger the network decisions, and then they manually analyze the patterns, and they say, okay, that looks like rotation equivariance, that looks like scale equivariance. Yeah, and they show that a lot of different symmetries are learned. This. Yeah, so all of these methods are great, but sometimes it can be very challenging to apply them practically. For the first family of methods, obviously, they rely on architectural modification, so they're very hard to apply to off-the-shelf methods. You cannot just take any network and analyze it. You will need to modify its layers. The methods which rely on predefined transformations are obviously require some prior knowledge of symmetries, and it then turns into some chicken-egg problem. So you want to know about the symmetry, but to know about the symmetries, you need to have knowledge about the symmetries. And the manual identification of symmetries, it's a great method, but it requires human intervention. And often, even with human intervention, it's not obvious. For example, from the same paper, like these patterns, it's very not obvious what symmetry is this. So to tackle this, we propose LieGG, which stands for LieGG group generators. And LieGG is applicable to any off-the-shelf neural network. It doesn't require any architectural modifications. The only requirement is that the model is differentiable. It retrieves symmetries without prior knowledge, and it retrieves symmetries in the easily interpretable manner. And by that, I mean that we directly retrieve symmetry group generator. So on a high level, it works as follows. We have a data set and a neural network. With this, we form what we call network polarization matrix. And then with this network polarization matrix, we solve matrix equation to compute the group generator. And then we can take the generator and see how it includes our data, if it works. Yeah, so before diving deeper into theory, here is just a glossary of what we're going to discuss. So by symmetry group, we mean set of transformations that leave an object unchanged. Of course, the proper definition is slightly more involved, but let's keep it simple. So the LieGG group would be a symmetry group with a structure of differentiable manifolds. Lie algebra then is a tangent space to a LieGG group as identity. And we often need Lie algebras because they form vector spaces, and they're much easier to analyze than Lie groups. And also it's useful to know that there exists the group Lie algebra correspondence. That is to say is how you move from Lie group to Lie algebras, and you can do that through the folding mapping. Yeah. Oh, and also in this work by symmetry, we always need invariants. So yeah, I remind you that our goal is to retrieve flow symmetries, and by symmetries I mean invariances. And to do so, we make use of invariance condition for Lie algebras. So here on the right, you see just invariance condition for Lie groups, so normal invariance condition that we all used to. So we have some element from a symmetry group. Well, these elements somehow affects on the data, and it is the same as it doesn't. So this is just invariance condition for Lie groups. So this invariance condition is very non-trivial to analyze. It's very hard to just take this condition and say what G should be, like only from this. To tackle this, we'll move this condition from Lie group to Lie algebra, and we make the step by the group Lie algebra correspondence that was talked on the previous slide. And it turns out that if for Lie groups, this is very hard to solve, then for Lie algebras, it just turns into a null space problem. So here, the Lie algebra generator is just a null space, is in the null space of this matrix. And we know how to solve null space problems. Yeah, here is an algebraic form of how we would write it. So this is just an algebraic form of this matrix equation, where we have gradient of the network, we have our data, and we have the generator of the Lie algebra. And we compose them into the network polarization matrix. And then to find a null space, we can do singular value decomposition of the network polarization matrix, and then singular vectors with near zero singular values, they form a null space, and thus they are the generators of the symmetry group. One more note about symmetries acting on images. So before I was talking of how we retrieve symmetries, where x here is the coordinates of our data. So that would be the symmetries with respect to the coordinates. Images are slightly more complicated because the network takes an image as a function of intensities. So we cannot just directly find symmetries of the neural network with respect to of the images, because it will be symmetries with respect to intensity. But we want symmetries with respect to coordinates. We want the coordinate change, which leaves that prediction unchanged. So to tackle this, we're told that the image itself is a function from coordinate space to the intensity by intensity function. And then we can define the whole pipeline as we have some coordinate grids. With intensity function, we move this coordinate grid to intensities, then our network takes intensities, and then we perform all the same steps and all the previous slide and formulate the null space problem for images. It is mostly the same with this additional term being responsible for mapping between coordinates and image. And network polarization matrix would be, in that case, the matrix where in the rows you will have the same number of rows as number of samples in the data set, and in the columns you will have each element for each of the combinations of K and J index here. Yeah, if you have any questions, by the way, feel free to interrupt. Yeah, so here is an example of how it would work for rotations. So we have our network polarization matrix. We perform singular value decomposition of this matrix. We identify singular value which is near zero and the singular vector which corresponds to the singular value. And this is our null space basis. Then we can just take this null space basis, we can exponentiate this null space basis, and we just apply it to other data sets. And yeah, it turns out that it is like rotation here. So yeah, the pipeline is the following. First, we need to construct the network polarization matrix. Then we compute singular value decomposition of this polarization matrix. Then we retrieve singular vectors corresponding to near zero singular values. They are the generators of our symmetry groups. And then also, as I will show on the next slide, we can further analyze the structure of the network polarization matrix to evaluate different properties of neural net, different symmetrical properties of neural networks. Yeah, so the symmetry variant, we propose two measures to evaluate symmetrical properties of neural networks based on the network polarization matrix. We show that the minimum singular value of the network polarization matrix, it will just tell you how the network is invariant to so you have some directions of invariance that some symmetry group generators have learned. So it will tell you what is the best possible invariance for this network if you assume that the symmetry is some Lie group. And it's also interesting to know that this quantity, it does not depend on the symmetry group generator. So we don't need to know symmetry to evaluate this. And the second is symmetry bias. The symmetry bias is, so when you retrieve some generator, you can actually, so if you know true generator, if the true generator is given to you, then you can compare how those two are close together. So this metric we would call symmetry bias. And again, with rotations, high symmetry bias would indicate that the rotations are noisy. They can be like some shearing or some like scaling all the way. And low symmetry bias is just clean rotations. Yeah,
I have a question. How do you generate these visualizations from the generators?
Yeah, so we had a lot of networks.
Mm-hmm.
So like for the future experiment, we just trained a lot of networks to average the results. And here for each of the network, we just plot one circle. And then this density is just kernel density of all of these circles. So yeah, the spoiler is for shallow networks. Here's like multiple shallow, I guess it's like 50 shallow networks. And this is like 50 deep networks. Yeah, let's move to experiments. So the first experiment is just a sanity check. Let's take a simple problem where we know what symmetry is and see if our networkalization matrix gives us something meaningful. So here at the data we have coordinates, and as a function we have the following function, which enjoys all type symmetry, like rotation symmetry in each of its arguments. And we train, in this case, we just train a simple multilayer perceptron to approximate this function. And we evaluate the symmetry variance and symmetry bias with respect to rotation. So here is a plot of the spectrum of networkalization matrix. So these are just singular values. And as you can see, at some points, the singular values drop to 0, which means that the null space in those singular values. So the null, this networkalization matrix enjoys some null space. And if you look at the singular vectors, which correspond to the singular values, you can identify what symmetry is. And here we evaluate the symmetry by the respect to rotation symmetry, because we know that this is a rotation invariant task, and we see that indeed the network learns rotations.
Are these residual errors in the last 10 singular values just numerical instability, or
I think it is twofold. Like, yeah, of course you can always attribute it to numerical instability, but in practice we noticed that you don't need to have a strict null space. You don't need to have like absolutely 0 singular values. So usually, if it's like as long as you see that it is like somewhat meaningful, and if you compare it with other singular values, it like somehow indicates appearance of the null space, then yeah, it works out.
Interesting. Yeah, because the bias seems to be really close to 0 or 0, and so then.
Yeah, so so it tells you that the best symmetry the network learns is pure rotation.
Yeah.
But the network is not fully invariant to this symmetry.
Yeah.
So I guess this is kind of a side effect of that we don't assume any symmetry when we do that. So we evaluate this. So this is like invariance error with respect to learned transformation.
Yeah.
So
exactly.
it doesn't have to be 0.
No.
Yeah, next we have experiments for the rotation needs. Here we just have rotation needs data set, and we feed the network to classify the images. And again, we evaluate it based on symmetry variance and symmetry bias with respect to rotation symmetry. So here we also train 2 types of networks. We have shallow 2-layer network, and we have deeper 6-layer perceptron. And we train them, we plot the results, and we sample some of the symmetries that we extracted. And yeah, we can see firstly that the shallow network learns noisy symmetries, which indicated by the higher symmetry bias. So that is to say, you can, here is a pipe, and if you rotate it, it doesn't like exactly stays as clean rotation. Like it scales a little bit, it stretches a little bit, but the deeper networks, they really learn clean rotations. So yeah, in that sense, you can also take this method and compare which of the network learns better symmetries than others.
So I think we briefly discussed it at some point, but do you have an intuition for why the deeper networks are better learners of exact symmetries? Because the number of parameters is the same, right, for these networks, or no?
Yeah, let me answer on your question the next slide.
Yeah, okay.
Yeah, so we also noticed that it's very interesting, like, okay, symmetrical properties are kind of depend on the architecture. So let's just test how different configurations affect on the symmetries. So here we test the networks with different depths, different widths, and different number of parameters. Again, the same task. We evaluate symmetry variance and symmetry bias. And yeah, we'll plot all the results. So a few takeaways from this plot. So the first one is the over-parameterized networks. They learn symmetries better than under-parameterized network, which is probably not surprising. But it's also interesting because we thought like, okay, why it can happen? Maybe it's because networks, they just become more accurate and they are able to catch symmetries better. So we made a correlation plot of symmetry variance and symmetry bias accuracy, and it actually gave only like mild estimate of accuracy. So there is no correlation, there is no strict correlation between symmetry variance and symmetry bias and accuracy. So it means that you can have two networks with the same accuracy, but the one with more parameters usually will be better symmetry learner than more shallow network. So this is the conclusion regarding to the number of parameters. Yeah, and we also noticed that if you fix number of parameters and if you vary depth, so you have like 1/68,000 of parameters, you can make a network deeper, or you can make it more shallower but wider. In that case, deeper network would learn better symmetries than wider networks. And yeah, this is intriguing results. We were also wondering why that happening. So the high level answer would be that symmetries, they are usually defined on the level of labels. And labels are often the most abstract representation of data. So more depth you have, closer you to this maximum level of abstraction. But it also could be like an implicit bias of optimization, for example, because yeah, we know that a lot of interesting stuff is happening with deeper and over-parameterized networks, and now people attribute it. Now people actually learn that it's not magic, it's happening because these are inductive biases of gradient descent. So yeah, the next question we asked, okay, we kind of understood that symmetry learning depends on the configuration of the network. Let's now try to understand if the learning regime somehow affects symmetry learning. So here we have three learning regimes. The black one is a baseline. It's just a plain end-to-end training. The blue one is a fine-tuning. That is to say, we extract some subnetwork, we train this subnetwork, and then we fine-tune all the network together. And we also have a layer-wise training as a third training regime, where we extract some network, we train it, and then we freeze the weights and train the rest. So again, we have plots for symmetry variance and symmetry bias for the rotation needs. So firstly, we observe that, okay, the training regimes, they don't really include symmetry bias. So in all of the cases, the network learns more precise symmetries as you go deeper into the layers. And here is, by the way, on the x-axis, you have the index of the layer. So that would be like symmetry variance after the fourth layer, and same with symmetry bias. So that could be probably attributed to the same, as we discussed on the previous slide, the deeper networks are better symmetry learners. But regarding symmetry variance, we observed like some very interesting results. That you can use various training regimes, various training strategies. We actually even try to vary like weight decay and like different learning rates, but always in the ultimate and penultimate layer, the symmetries converge, the symmetry variance converge to more or less the same values. And yeah, this is very interesting result, I think. I barely don't fully understand why this is happening, where yeah, well, like actively working on this right now. But I think it also can be attributed to the bias of the Stochastic gradient descent and such phenomena as narrow collapse in the representations. Yeah, so to sum up, we introduced LieGG, a method to retrieve symmetries learned by neural networks. To do so, we use the group Lie algebra correspondence to formulate symmetry extraction as a null space problem. We propose symmetry variance and symmetry bias to measure symmetrical properties of neural networks, and we studied symmetrical properties of networks with different configurations. Yeah, that's it.
Thank you. Very nice. a super interesting talk. I have a couple questions. I guess the first one is, so usually how people use symmetries in data is you sort of have an assumption about the symmetries that are contained in your data, and then you build a network which is equivariant or invariant to these symmetries. You take sort of a different approach, saying we don't know which symmetries are in our data, we're going to extract those. With this method, then could you, for example, use this to okay, so you extract, for example, rotation symmetry. So now you know these exist in your data. So then you use a network which is equivariant to rotations. Is it like a way of extracting symmetry in data to I don't know?
Yeah, I think
reintroduce these inductive biases. And then I guess my follow-up question is, are the symmetries that this method extracts, do you know whether these contribute most to performance? So is it a question of these symmetries are easier to extract for the network or to learn for a network, or are these symmetries also the ones that increase the performance of the network the most, or being invariant to these symmetries?
Okay, let me start with the first question. That is, can we discover the symmetries and then reintroduce them to the network? Yeah, I think this is kind of like initially what we plan to do with this, but then we also run into this problem that comparing to this method is two shots. So you need to train a network to extract symmetries, and then you need with the symmetries to construct another network.
Yeah.
So it's kind of like not end to end. I think, yeah, the possible direction for future work is to implement it as a sub-module for the layer. And then you can use some parameterization of your weights depending on the symmetry group generator. Yeah, and if it's all differentiable, I guess it should work, because in principle, all the operations that we use here are differentiable. SVD is differentiable. So yeah, we have a differentiable way of parameterizing our basis for our weights based on this generator. That, yeah, I think it can work.
Yeah.
And the second question was if the network learns symmetries because they're easier to learn, or because they are important for solving the task. Yeah, this is a good question. I think that well, I have no intuition about either some symmetries are harder to learn than another. If you take just completely unconstrained networks, I would be very surprised if, for example, translation would be harder to learn than rotation. But on the other hand, yeah, so when you want to classify, when you want to feed the model on the data which you know is rotation invariant, so the perfect function would be rotation invariant. So here the accuracy would be hardly tackled with its ability to learn symmetries. So I think it's more that it learns symmetries because they're important to solve the task.
Yeah, that's right. Cool. You guys have any questions?
I was wondering if you ever tested your method with an equivariant network.
Yeah, so we focus on invariance, not equivariance. So we tested it on invariant network. We tested it on well, if equivariant perceptron is called equivariant, but it's actually invariance. Yeah, we tested in this where the rotation symmetry is hard-coded, and we applied our method just we sample random data, we fit into this a priori invariant network. We record symmetry variance and symmetry bias, and it just gives a zero symmetry variance with respect to rotation group and zero symmetry bias with respect to rotation group straight away.
So in your first example, did you see then that the null space was exactly null instead of like the
Yeah.
Is there any questions? No questions. Maybe people online, if there are any questions, now would be a good time to speak up. Otherwise, I will have some more. So I was wondering, so this method, you built this polarization matrix, and it depends on the size of the data set, right? So how does it depend on dimensionality of the data, and is it feasible? Is this method feasible for ImageNet size images, for example?
Yeah, so the computational bottleneck here would be, well, like obviously need to compute the gradient of your network, but I think even for the largest network now, it's not very hard. So the computational bottleneck is computation of FPD.
Yeah.
I think the good stuff is that FPD is pretty well optimized in all of the libraries that were used. So yeah, I think it should be. It's more like memory requirements than computational power requirements. So you need to have a lot of memory if you want to use a large data set like ImageNet to allow SPD to work.
Yeah.
But we also had experiments when we don't take all of the data set, but we take like a fraction of the data set. So it turns out that if we use just 5% of the data set, it already kind of gives you a very good estimate of the symmetry. So yeah, I think it scales really well in this regard.
And do you have intuition? I think one of your slides also contained an image from a paper by I think Louis Wang on the approximate equivariance. Do you have intuition for how well your method? Yeah, this one. So the lower, I think the point of this image is to show that some symmetries are only approximate. Do you have an intuition for how well this method will work in those cases? So if you're does it then extract these approximate symmetries?
Yeah, in that case, you can extract symmetries and you will record, for example, the same symmetry variance, but you would have different symmetry bias.
Yeah.
So yeah, here you will have obviously like zero symmetry bias. Here you will have non-zero symmetry bias.
Yeah. So the symmetry bias would then tell you how different the approximate equivariance is from the exact equivariance, which could be very interesting because in this case, like your data is actually approximately invariant. Like symmetry bias, I think sort of is more a measure of how, or you probably introduce it to see how well the network learned the symmetry, right? From the data.
Yeah.
In this case, the data is actually not perfectly symmetric. So it could be also a measure of how imperfectly symmetric the data itself is in some sense, maybe. So I guess it's hard to distinguish.
Yeah, exactly. It's hard to distinguish because, like, for example, okay, so that maybe seem like approximately invariant, but I guess if you interpolate it further for the next hundred of time steps, it will be like highly asymmetric. And then for many cases, you can imagine that you don't know even the generator of this symmetry.
Yeah.
So if you don't know the generator, then you cannot compute the symmetry bias.
Yeah.
So in that sense, yeah, you will retrieve the generator and you will be able to see that it is very far from the rotation.
Yeah.
Or like, for example, that it evolves to be very far from the rotation.
Yeah.
So yeah, you would be able to say that it kind of like diffused rotation when you put your time to the limits, something like that.
We just briefly also discussed equivariance. Do you have an idea for how this method could be extended to learn for equivariant problems?
Yeah, I think the same approach could be used for equivariance, though like for invariance, it's pretty straightforward. It's pretty straightforward to construct invariance criteria for Lie algebras. For equivariance, we will also have like G-1 here. And in that case, the mapping between the Lie group and Lie algebra, it seems would not be that simple. Though I think that you will end up in the Lie algebra where the symmetry generator you still would be able to compute, but it will be some like iterative method probably where you will approximate it somehow. So yeah, I think it is like the intuition of this method is definitely applicable to equivariance. Practically, it might be a little bit more computationally involved to compute equivariance.
Are there certain Lie groups for which this method doesn't work, or does it in principle work for all? So got the question about for non-simply connected Lie groups. Does it also work if you have reflection symmetry, for example?
I think, yeah, so the requirements to form the Lie algebra to your Lie group is that your Lie group is a smooth manifold.
Yeah.
So if you have reflection, it's not a smooth manifold. It's like highly disconnected. So in that case, Lie algebra, which is a tangent space to your manifold, will be like way off the manifold itself. So yeah, I don't think it will be. Yeah, I think it's only applicable. The assumption that we made that if it's a Lie group with which gives us with some smooth manifold structure, really underlying it.
Very nice.
I have one question. In your example, you gave an example with one singular value, and you showed that gave a generator of rotations. But in your experiments, you see many singular values in the null space. Did you also see or investigated the differences between those generated and what kind of?
Oh yeah, definitely. So yeah, so I mean here, for example.
Yeah, what kind of generators it gave?
Yeah, so these are all symmetric matrices, and because this is like 5-dimensional rotation, those are just rotation around different axes. So yeah, they're all so because this is SPD, they are all formed in the way that they are orthogonal to each other. So these are orthogonal symmetric matrices which corresponds to rotations around different axes.
And combination of axes. Because there are more than 5.
Yeah. So it's 10 orthogonal ones, and like almost orthogonal because the singular values are not exactly 0. Okay, if they were exactly 0, they would be exactly orthogonal. Yeah, so each singular vector is a basis in the Lie algebra space. Element of the basis.
Very interesting. I think I ran out of questions.
Okay.
Answered them all very well. If there's no more questions online or from the audience here, then we can wrap it up.
Thank you.
Thanks again. Yeah, very nice presentation. I'll stop the recording here.